In this video, we're going to talk through the notes for section 3.2, which is called Orthogonal Expansions. The expansion that we're really interested in is what we call a Fourier series. A Fourier series is an infinite sum of sines and cosines of the form you see here. We have this a0 over 2 term, which is the constant term, plus the sum n equals 1 to infinity of these terms, which we call the nth harmonics. So it's an times cosine of n pi x over L plus bn times sine of n pi x over L. In a sense, this a0 term should go in here. It's when n is equal to 0. But we have a slightly different value for it because of that 2. That's just in order to make the formulas work out right. We'll see later when we actually write down the formulas, although we've seen them before in an earlier set of lecture notes. So this L here we'll see is the length of a certain interval. On the set where this series converges, it defines a function f. In this case, the series is called the Fourier series for f. So a natural question is what functions can be represented as a Fourier series, and how do we compute an and bn in this case? Well, first let's talk a little bit about periodicity. Recall that a function f is periodic with period t, if f at t lowercase t plus capital T is equal to f at lowercase t for all lowercase t in the domain of f. That's what it means for a function to be periodic with period capital T. The functions that take theta to sine of theta and theta to cosine of theta both have period 2 pi. That is, one period can be represented as the interval minus pi to pi. Suppose that theta is equal to n pi x over L. Now, of course, that's not randomly selected. This n pi x over L is, of course, the same n pi x over L we see in the Fourier series. Then sine of theta and cosine of theta complete a full cycle when theta goes from minus pi to positive pi. So instead of theta, we put the n pi x over L, and we solve for x, so to speak. You multiply by L, which we're assuming is the length of an interval, so it's going to be positive. You divide by n times pi, and what you end up with is that one full cycle is completed when x goes from minus L over n to positive L over n. So the functions that take x to sine of n pi x over L and x to cosine of n pi x over L both have period 2L over n. 2L because the distance between these two numbers, minus L over n and positive L over n, is 2L over n. So they both have period 2L over n. If a function has period 2L over n, then it also has period 2L. We can see this by just repeatedly applying 2L over n. Since it's periodic with period 2L over n, f at little t is equal to f at little t plus the period. But that is equal to f at t plus the period, so 2L over n 2 times. And then you can just keep adding in periods over and over and over again until you do it n times, and then 2L over n times is just 2L. So the important thing here is to understand that the functions that take x to sine of n pi x over L and x to cosine of n pi x over L all have period 2L for any choice of n, regardless of the choice of n. Now the smallest period is called the fundamental period, and we're not saying that the fundamental period is 2L. Just like sine and cosine have period 2 pi, they also have period 4 pi, but the fundamental period is 2 pi. Here we're not saying that the fundamental period is 2L, we're just saying they're periodic with period 2L. So why is this important? That's important because it means that if a function is equal to a Fourier series of the form that we wrote above, namely if a function f is equal to a Fourier series that looks like that, all of the terms have period 2L. So that means the function itself must have period 2L. So that's what we've written here. if a function is equal to a Fourier series of the form above, it must have period 2L. So not any function can be written as a Fourier series. It must be a periodic function. Now, in actual fact, what we'll do is we'll just look at a small interval and we'll extend the function to a periodic function outside of the interval, even though what we're really interested in is some closed bounded interval. We'll see that when we look at examples. So the next question is, how do we compute the coefficients in that Fourier series? So suppose that f is equal to that Fourier series that we wrote above, this one right here. A natural question is, how do we find the coefficients? Well, basically what we do is we use a certain property of sines and cosines known as orthogonality. And we've expressed that in the terms of this theorem here. So what do we mean by that? So suppose that L is some fixed positive number. Then if you integrate from minus L to L of cosine n pi x over L times cosine of k pi x over L with respect to x, then you'll either get 0 if n is not equal to k, or if n is actually equal to k, you get L. You have the same sort of statement if we replace cosine with sine, as you can see here. So here we're looking at the integral from minus L to L of sine of n pi x over L times sine of k pi x over L dx. If n is not equal to k, you get 0, but if n is equal to k, you get L. In other words, if you take any of these sines and cosines and integrate them against other sines and cosines in the same set, you get 0. The only way you get non-zero number is if you integrate it against itself. Now we also could integrate sine against cosine, but no matter which choice of n or k you pick, you'll end up with 0. The integral from minus L to L of cosine n pi x over L times sine of k pi x over L dx is always equal to 0 for any n and k, even if n is equal to k. Now, this isn't true whenever you integrate sine and cosine together over an interval. It's true because of what we're integrating. The arguments are of this form, n pi x over L, and we're integrating from minus L to L. So that the presence of that L is crucial. The presence of the n is crucial for this to work. So these computations are similar to ones that we've done in a previous lecture. So we won't go through them here. We will make use of them, however. We say that this collection of functions, sine of n pi x over L and cosine of k pi x over L for all n and k, is an orthogonal set. It's orthogonal because when you integrate them against each other, you get 0, but when you integrate a function against itself, you get something which is non-zero. Note also that if you just simply integrate the functions, so if you integrate sine of n pi x over L from minus L to L, you're going to get 0. Same for cosine. The integral of from minus L to L of cosine n pi x over L dx is going to equal 0, regardless of n. This will be useful when we're making our computations. In particular, what we're saying is that when we integrate against a constant, you get 0. So here's our theorem. If f is given by the Fourier series above, in other words, if f is given by this Fourier series right there, then the way to compute the coefficients, an and bn, is given by integration against these sines and cosines. So if you integrate from minus L to L of f at x times cosine of n pi x over L with respect to x, then you're going to get L times an. So the L that you get is from right here or here, depending on which one of these you're doing. So that means we have to divide by L, and that gives us our an. We'll actually do these computations so you can see where all of this stuff comes from. We also have a similar one to find the bn. Bn is equal to 1 over L times the integral of minus L to L f at x sine of n pi x over L dx. And you can sort of see where this is coming from if you just look at the formula. So if we integrate this Fourier series against cosine of k pi x over L, because of the orthogonality relation, whenever it integrates against the sign, you're going to get 0. When it integrates against a constant, you're going to get 0. When it integrates against another cosine, you're going to get 0 unless n is equal to k. And that's exactly what we've shown here in the proof of the theorem. So we're just going to compute this directly. We'll add in the 1 over L later, so we're just going to integrate from minus L to L f at x cosine of n pi x over L dx. That's what we have here. So notice we've just replaced f at x with its Fourier series. That's how we defined f. So we just replaced it there. The next thing that we do is we distribute the cosine. So this cosine, n pi x over L, we just distributed it to all of these terms here. Okay. Notice that we're summing over k, so we have k here and we have a k there. Okay. Now, this first term, you can take the a0 over 2 out of the integral, and then you're just integrating cosine of n pi x over L from minus L to L, and we just mentioned that that was equal to 0. We just showed that. We just discussed that. So this term is 0. Similarly, here we're integrating sine times cosine, and we established that that was 0 as well. Here we have what I'm writing as delta nk. So delta nk is equal to 0 if n is not equal to k, and it's 1 if n is equal to k. So this integral of cosine k pi x over L times cosine of n pi x over L, we established that this was 0 if n was not equal to k, and it's equal to L if n is equal to k. So that's why I wrote it this way, delta sub nk times L. So in other words, it's equal to L, this whole sum. If you add all of this stuff together, all of these terms are 0, all of these terms are 0, and all of these terms are 0 except for 1 when n is equal to k. And then you get a 1 there times L. So you get an L from that integral. So every term cancels except for the one where k is equal to n. Now there's an ak in front of here, an a sub k. So you're going to multiply this a sub k times 0 unless n is equal to k, and then you're going to multiply it by 1 times L. So that's why you have an an times L here. So then we just divide by that L, 1 over L here, just 1 over L here, you'll get L over L there, and those will cancel. And then you get the coefficient a sub n. Now, a similar computation works to show that if you integrate from minus L to L of f at x sine n pi x over L dx, you get b sub n times L. The computation is exactly the same, or essentially the same, so I won't write it all down. What about the case where n is equal to 0? Well, in the case where n is equal to 0, cosine of n pi x over L is equal to 1. So when you integrate f at x times cosine of n pi x over L, you're just integrating f. So that's the integral from minus L to L of f at x dx. So again, we've just replaced f with the Fourier series which defines it, and now we can just integrate each one of these terms. Here we're just integrating a0 over 2 from minus L to L, and here we're integrating cosine, here we're integrating sine. We've already established that if you integrate cosine n pi x over L, you get 0. And same with sine. That's just up here a little bit. That was right here. If you integrated sine n pi x over L or cosine n pi x over L, you just got 0. So that's what these terms are here. That's what we're getting here. We're just integrating this thing and getting 0. That's 0. But what about What about this term right here? We're just integrating a0 over 2. So that's a constant. So if you integrate it, you just get the constant back times the length of the interval, which is 2L. So that's why we have a0 over 2, because when you integrate it, these two cancel, and you just end up with a0 times L. So once again, you just divide everything by L, and then you end up with a coefficient. But that's why when we write down our Fourier series, like we have here, that's why we have a0 over 2 instead of just a0. That's why we have a0 over 2 there instead of just a0. It's to make these computations work. It's to make these computations work. We want to have the same formula. For an arbitrary function f that is integrable on this interval from minus L to L, we can define the Fourier series of f using the same formulas. Now in this case, we're doing something slightly different. So in the previous case, we were looking at a Fourier series and we were calling that f. That's not what we're doing here. We're letting f be given. So f is given, and then we're going to define a new series, which we're calling the Fourier series of f, by letting that new function be equal to this expression here, where a0, an, and bn are all given by these formulas. These are the same formulas. But before, what we were doing is we were defining a function in terms of a Fourier series. And what we said was, oh, we can find the coefficients an and bn using these formulas. But now we're not doing that. What we're doing instead is we're defining a new function. And we're defining a sub n and b sub n to be equal to these expressions. So before, what we were doing is we were identifying a pre-existing an using some integration technique. Now here, instead of identifying a pre-existing an and bn, we're defining a new an, and we're defining a new bn to be equal to whatever these integrals are. So we're given a function f, and we're defining a new function, which we're calling the Fourier series of f. So the reason I'm mentioning this over and over again is that there's no reason to assume that f is actually equal to its Fourier series. We would like for that to be the case. We want the Fourier series to in some way represent f. So a natural question is, when can we say that that's true? When is it the case that a function is in some sense equal to its Fourier series? And we'll see that that isn't always true. It isn't always the case that a function is equal to its Fourier series, but often it is in a sense that is useful to us. Now, in order to make sense of any of this, we're going to speak about Fourier series more generally. So we're going to talk about something called the general Fourier series or the generalized Fourier series. And this is a very abstract discussion. All right, so we're going to begin with some generality. So we're looking at an interval AB. So all we know about this interval is that it's closed bounded interval with a less than b. And a and b are finite numbers. So if we're going to define the set L superscript 2 of the interval AB or over AB to be the collection of functions which we call the L2 functions or the square integrable functions. And these are the functions f from ab to r such that the integral from a to b of the absolute value of f at x squared dx is finite. So we're not saying that f can be integrated, we're saying that f squared can be integrated. So this is the collection of what we call square integrable functions, or we just call them the L2 functions. We define what we call the L2 norm of a function on f on ab to be what you see here. So the L2 norm of f is equal to the square root of the integral from a to b of the absolute value of f at x squared dx. We really don't need that absolute value there since we're squaring it. However, even though we're talking about real valued functions, all of these definitions make sense for complex valued functions. So that's why I'm putting the absolute value signs there, because even if f is complex valued, then this definition still makes sense. You look at the magnitude and then you square it. So the idea is that you look at a function f, you look at the magnitude, you square it, and you integrate that, and then you compute the square root. So this is what we call the L2 norm of f. So note that f is an L2 function if and only if its L2 norm is finite. For computations, it's often more convenient to not compute the L2 norm, but to compute the L2 norm squared, because if you do that, you don't have to worry about the radical symbol. So that's something to keep in mind when we're doing computations. We're interested in the norm, but very often we'll compute the norm squared, just for computational convenience. So here's an important remark. L2 AB, the set of L2 functions over AB, is an inner product space with inner product defined by integration. So the inner product of f with g is equal to the integral from a to b of f at x times g at x dx, where f and g are both square integrable functions. Recall that an inner product satisfies the following properties. First of all, it's symmetric. The inner product of f with g is the same as the inner product of g with f. Also, it satisfies bilinearity. That means it's linear in each argument. Now really, since it's symmetric, we only need to say one of these, because if you know that it's linear in its first argument, you can always use symmetry to swap the second and first arguments and show that you have linearity in the second argument too. So really, just one of these is sufficient. We really only need one of those. But we call it bilinearity if it's true in both. We also want the inner product to be positive definite. That is, that if you compute the inner product of f with itself, you're always going to get something non-negative. And in fact, it's always non-zero unless f itself is 0. So these conditions are required for a real inner product space. If we allow for complex valued functions, the properties are slightly different. So here's an important note. There's a relationship between the inner product and the norm. So if you look at the inner product of f with itself, then that's the integral from a to b of f times itself. But that's actually just the integral of f squared over the interval. So that gives you the L2 norm of f squared, because notice that there's no radical over the integral. Okay, so let's look at some examples. Consider the set L2, 0, 1. This is the set of square integrable functions on 0, 1. We want to compute the L2 norm and the L of both f and g for certain functions. So let's say that f is x squared and g at x is equal to e to the x. So we want to compute their L2 norm. So we're going to start by computing the square of their norms, and then we'll just take the square root of that. So the square root of, or rather the square of the L2 norm of f is the integral of x squared quantity squared from 0 to 1. So that's just x to the 4th from 0 to 1. You integrate it using the power rule, and you get x to the 5 over 5 from 0 to 1. And that's 1/5. So that tells us that the L2 norm of f is 1 over the square root of 5. Similarly, if you compute the L2 norm squared of g, that's the integral of e to the x quantity squared, or e to the 2x. So we integrate that, we get 1/2 e to the 2x from 0 to 1, so it's 1/2 times e squared minus 1. So if you compute the square root of that, you get the L2 norm, which is 1 over the square root of 2 times the square root of e squared minus 1. The inner product of f and g is given by the integral of their product. So the inner product of f and g is equal to the integral from 0 to 1 of x squared e to the x dx. Now, in order to evaluate this, we need to use integration by parts twice, but assuming I've done my computations correctly, I get e minus 2 in the end. Before we go on to the next page, there is something I should say about the positive definite condition, in particular when we talk about this f is equal to 0. When we talk about a function being equal to 0 in L2, we have to be slightly more careful than we normally think about that. So normally when we write f equals 0, we mean that f at x is equal to 0 for all x. Now in terms of the integral, if I change the value of f from 0 at one point, so f is 0 everywhere except for one x value, then when I integrate it, the integral can't tell that. The integral doesn't notice what's happening at just one point. So when we talk about a function being equal to 0 in L2, we don't mean that it's equal to 0 everywhere necessarily. There's a certain type of equality which is called almost everywhere equality. So we can say that f is equal to 0 almost everywhere if the integral thinks that it's 0. Now, a discussion of that is a little bit beyond anything that we can get into, so we're just going to skim over that. But just keep in mind that when I say that a function is equal to 0, I might mean that the integral thinks that it's 0, and that any time the integral is computed over any interval, the integral will always give you 0. But let's not worry about that too much. So let's look at these examples. F at x equals sine of pi x and g at x equals cosine of pi x. Show that f and g are in L2 over 0, 1, so they're square integrable, and compute their inner product. Now, given what we've done before, it shouldn't surprise you to learn that their inner product is 0. So we can compute their L2 norm. So if we start by looking at their L2 norm squared, so the L2 norm of f quantity squared is just the integral of sine quantity squared. And of course, if we compute that, we end up with 1/2. That shouldn't surprise us. We've seen something like that already. So we integrate that, and we get 1/2. So that means the norm is 1 over the square root of 2. If you integrate g squared, so we have cosine squared, we see that that's also equal to 1/2. So that means the L2 norm of g is 1 over the square root of 2. Their inner product is the integral of sine times cosine, which is, of course, 0. When the inner product of f and g is equal to 0, we say that f and g are orthogonal. And we can normalize a function by dividing by its norm. So if some function g is equal to f at x over the norm of f, maybe I shouldn't call it g since we're already using g for something else. What do we want to call it? We can call it h. So if h at x is f divided by its size, then the L2 norm of h is going to be equal to 1. So in our last example, the size of the vectors was 1 over the square root of 2. So if we divide by that size, that means we're multiplying by the square root of 2. So we have the square root of 2 times sine of pi x, and the square root of 2 times cosine of pi x are normalized vectors. They're normalized orthogonal vectors because they're orthogonal to each other. If we have a collection of mutually orthogonal vectors, then we call it an orthogonal set, or an orthogonal system. If it is true that all of the sizes are 1, then we call it an orthonormal set. So orthonormal, the ortho means orthogonal and the normal means size 1. So we call it an orthogonal set or an orthogonal system. We'll use that term a lot. So set or system. So L2AB is an example of an infinite dimensional vector space. We call it a function space. So it behaves in some sense like finite dimensional vector spaces, but there is a lot more to it than that. And by that, I don't just mean there are a lot more elements. There are certainly infinitely many. And you can't find a finite collection of functions that forms a basis. So there's no collection of functions, f1, f2, up to fn, in L2, such that any f can be uniquely expressed as a linear combination of those functions. is it possible to find an infinite collection of functions in L2 such that any f can be written as a linear combination of this infinite collection for some sequence of scalar coefficients ck? And the answer is yes. But you have to be a little bit more careful. With infinite sums, we have a question of convergence. So does this sum converge, and does it converge to the function f? And in what sense does it converge? With infinite sums, we have to address these questions. So we say that this sum, ckfk, converges to f in L2, or in the L2 norm. So it converges in L2, or in the L2 norm, if the limit as n goes to infinity of f minus this, what we can call a partial sum, goes to 0, if the norm of that difference goes to 0. So a norm measures distance in some sense. So what we're going to look at is we're going to look at a sum, an infinite sum. And we're going to define a sequence of partial sums. S sub n is equal to the sum of k equals 1 to n of this ckfk. So what does that mean? That means S at n evaluated at x is equal to the linear combination, the sum k equals 1 to n ckfk. So it's the linear combination of the first n of these terms. So Sn is an nth partial sum. So what we want to say is we want to say that this series converges to f in L2. So in L2, what that means is that the norm, the L2 norm, needs to be going to 0. Because in L2, we measure distance, we measure size using the L2 norm. So we want to look at the size of the difference. We want to measure how far they are away from each other. And we want to look at this distance. Now, if this distance is going to 0, then we say that the sequence of partial sums converges to f in L2, in the L2 norm. Now in your book, they don't use that subscript L2, they just use the norm. I'm putting the L2 there just for emphasis so that way we know exactly what we're talking about. So if the L2 norm goes to 0, then the L2 norm squared goes to 0. So we write that out here. So the limit as capital N goes to infinity of this L2 norm squared. So that's the integral over AB of f at x minus Snx quantity squared dx. This is called the mean square error. So the mean square error will denote by e sub n, lowercase e sub n, is just equal to this quantity. It's the integral of the difference squared. So the mean comes from the fact that you're integrating, and it's the square error because you're looking at the error and you're squaring it, and then you're computing some integral average. So if we write that out in terms of the ck's and fk's, it looks like this. So it's f at x minus the partial sum from k equals 1 to n of ck fk, quantity squared, so you're looking at the error squared, and then you're integrating it. This is not the same as the pointwise error. So the pointwise error is what we're calling capital En, and that depends on x. So at each x you measure the difference. So you're looking at the difference between f at x and Sn at x at a given point. That's the pointwise error. The pointwise error measures how far Sn at x is from f at x at each point. So you say that Sn converges to f pointwise if for each x this pointwise error goes to 0. So if the pointwise error goes to 0, that means that for a fixed x, you compute the limit, and for a fixed x, Snx is just a number. So for each x, you have a sequence of numbers which converge to f. That's called pointwise convergence. And that's what I have written here. Pointwise convergence means that for each fixed x, the sequence Sn at x converges to the number f at x. So this is just convergence of numbers as we have always known it. Convergence in L2 is a little bit more sophisticated, it's a little bit more subtle, because what that means is that the mean square error goes to 0. So the mean square error is an integral average of the pointwise errors. So you look at the pointwise error squared and then you integrate it. Integrals have a way of averaging things out, so that's why it's called the mean square error. So Sn converges to f in L2 if the mean square error goes to 0 as n goes to infinity. So convergence in L2 is also called mean square convergence. And your book usually calls it mean square convergence. I'll call it that, and I'll call it L2 convergence. Even if the pointwise error goes to 0, so even if you have pointwise convergence, it might not be true that you get mean square convergence. Let's look at this example. So suppose that you've computed the pointwise error. And suppose that you found that the pointwise error is equal to n if x is between 0 and 1 over n, and 0 otherwise. So you can see that we've drawn a couple of pictures here. So when n is equal to 1, you get this, the graph is this square region here. It's not the whole square, it's just that it's this line. So when n is equal to 1, the pointwise error is 1 for x between 0 and 1. So it's this. Now I just filled it in so you could see, because that area is 1. So the area is 1 underneath this curve here. Now when n is equal to 2, then what you have that e at nx is equal to 2 for x between 0 and 2. So that's here. The next one is 1/4, so that's when n is equal to 4. So when I say 1/4, I mean that 1/4. So when n is equal to 4, the pointwise error is equal to 4 if x is between 0 and 1/4. So that's this one. Notice that the area there, that's 4 by 1/4, so the area there is also 1. So the area underneath all of these is 1. So for each x, en at x, the pointwise error, so if you fix an x, the pointwise error is eventually 0 once n is beyond 1 over x. So 1 over x is always going to be between 0 and 1. So capital N is eventually going to be bigger than 1 over x. So that means that en at x goes to 0 pointwise. But en doesn't converge to 0 in the L2 norm. And why is that? So en, so we're integrating en from 0 to 1. So this is equal to, this en is equal to 0 once you're beyond 1 over n. So the integral from 0 to 1 is just the same as the integral from 0 to 1 over n, because en is 0 after that point. So it's non-zero between 0 and 1 over n, but it's 0 otherwise. So this integral from 0 to 1 is really just the integral from 0 to 1 over n. Now en at x is equal to n there, so it's n quantity squared. But if you compute this integral, this is a constant, so it's n squared x, where x goes from 0 to 1 over n. That's just n squared over n, which is n. And that goes to infinity. So you can see that even though the pointwise errors all go to 0, the mean square error does not go to 0. Now under certain conditions, the pointwise error going to 0 does ensure that the mean square error goes to 0. If, for example, you know that these pointwise errors are sufficiently bounded, so if they're what we call uniformly bounded in terms of n and x, then pointwise convergence does imply mean square convergence. So if you can show that these errors are all bounded by some constant for every x and every n, then you can draw this conclusion. You can see what's happening here is that our pointwise errors are not bounded. As n goes to infinity, this picture here, this line, this horizontal line, is just going to shoot up. So you don't have the boundedness that you might like. So that lack of boundedness is why the pointwise convergence doesn't imply the mean square convergence. So we wish to extend the idea of a basis to the function space L2. Now we will do this by using an orthonormal set, which we'll call f at k, or f sub k rather. So f sub k, which is a series of sequence of functions in L2, And we're going to assume that they're orthonormal. It's an orthonormal set. So that means all of the functions are mutually orthogonal to one another, and the size of each individual function is 1 in the L2 norm. So we're assuming that. But we also need an additional property, which is completeness. So an orthonormal set is called complete if the only function in f for which f comma f at n equals 0 for all n is f equals 0. So let's talk ourselves through that. So we have an orthonormal set f sub k. And the idea is that if you look at any f, you just grab an f in L2. And if you look at the inner product, f with f of n, you get 0 for all n. That means that f is orthogonal to every single fn in this set. So if f is orthogonal to everything in the set, it must be 0. That's what it means to be complete. So if you have an orthonormal set, f sub k, and then you find another f which is orthogonal to every single thing in that set, then you just add that to that set. And then you keep doing that until you exhaust it, and then the set should be complete. Now, that's an informal statement. The idea is that if it's complete, then that can't happen. If it's complete, you can't find another such function which is mutually orthogonal. This is basically like saying that you have a vector space where the basis spans. And if it doesn't span, then you can find some other vector which is mutually orthogonal to all of those vectors in your orthogonal set. Okay, so here's a theorem. If f sub k is a complete orthonormal system, then each f in L2 has a unique representation as a linear combination of these f sub k's, where here equality means convergence in L2. So when we say that f is equal to this sum, we don't mean that it's a pointwise equality. We mean that this series converges to f in the L2 norm, in the way that we were discussing earlier. Now the proof of this is quite abstract. We'll go through it, but it is a lot to take in. Okay, so what is it that we're trying to prove here? We're trying to prove that each f in L2 has a unique representation of this form, where f sub k is our complete orthonormal system. So, to prove this, we need to show that any f can be written as a sum in one and only one way. We want to show that it has a sum like this, and that sum is unique. So, first, suppose that f has a representation in this way, in the L2 sense. So when I say in the L2 sense, I just mean that this series converges to f. So let's assume that f has a series representation. So we claim that this is a unique representation. So we can integrate term by term. Now, that's something that we should verify, but assuming that we're allowed to integrate term by term, then if you integrate it against fn, so if you look at the inner product of f with fn, that's just the integral. So that's the integral of f against fn. That's the integral of the sum, because we're assuming that that represents f. That's our assumption here. Suppose that. So if we can integrate term by term, then we just take that integral inside here. And then we have this expression right here. Now, our assumption is that the fk's are an orthonormal system. So that means that this integral is equal to 0 unless k is equal to n. So in that case, this infinite sum only has one non-zero term. Every term is 0 except for the one where k is equal to n. So you just end up with one term when k is equal to n. So then you just have Cn times fn. But that's the norm of fn, or the norm squared, the L2 norm squared. But we're assuming that this set is orthonormal. That means the size of each one of these f sub k's is equal to 1. So that means that this is equal to 1 squared, which is just 1. So we have Cn times 1 is just Cn. So that means that if you integrate f with fn, you strip off the nth coefficient. So f comma fn is equal to cn. So that's a way to compute the coefficients. Now this tells us that the expansion is unique, because if you suppose that f has another expansion, then you can do the same thing. You can compute f inner product with fn, you can integrate f against fn, compute their inner product, and you'll get dn. If f is equal to this, if f has this expansion, then you just do the same thing, and then you get that the inner product of f with fn is dn, but you already know that it's cn. So cn has to be equal to dn. So that means that if you have one expansion like this, it must be unique in the L2 sense. So another question is, why are we able to integrate term by term? And to show this, we use something called the Cauchy-Schwarz inequality. So let's just scroll up here. So we're going to use this to show us that we can integrate term by term. So what is the Cauchy-Schwarz inequality? Now the Cauchy-Schwarz inequality says that if you have two functions in L2 and you look at their inner product, it's less than or equal to the product of their L2 norms. Now this is not a trivial result, it's very powerful. And it's also something which is surprisingly easy to prove given its importance. I could prove it here, but it's going to be an exercise. So I want to leave it as an exercise so that way you can enjoy proving it for yourself. So we're just going to take it for granted that this Cauchy-Schwarz inequality is true. But the idea here is that you can bound the inner product by the product of the norms. So let's take that for granted. So we assume that this series, the sum k equals 1 to infinity of ck fk, we're assuming that it converges to f. That's our assumption. So what does that mean? That means that if you look at the L2 norm of the f against its partial sum, minus its partial sum, remember that's what this is. This is s sub n at x. So this quantity right here is the L2 norm of f minus Sn. That's its L2 norm. Notice I'm not squaring it because there's the square root there. So we're assuming that this goes to 0. That's our assumption. So we're assuming that this series converges to f. So what that means is that this L2 norm, the difference in the L2 norm, goes to 0. That's our assumption. Okay. So now what I want to look at is I want to look at f times f sub n, because I'm trying to show that I can exchange the order of integration so that I can integrate term by term. Now if we just look at the partial sum, then I can look at the integral from a to b of fx fn minus the sum k equals 1 to n of ck times this integral from ab fk x fn x dx. Now if I have a finite sum, there's no issue about convergence, so that means I can integrate term by term. Okay, so what is this equal to? So I'm just going to take the integral out. Like I said, I can integrate term by term. So I'm just going to take the integral out, and so I'm going in the opposite direction. So if I take the integral out, I'm going to have f times fn minus the sum of the ck fk times fn. So I factored out the fn there. So this fn, I factored out this fn, and that's that fn. So that leaves us with fx minus the sum k equals 1 to n of ck of fk. Okay, so again, I just took the integral out, which I can do without worrying about convergence because this is a finite sum. Okay, so this is an inner product. See, this fn appears right here as well. And then here we have f minus the sum ck-fk right here. So this integral is an inner product of f minus the partial sum against fn. So it's the inner product of the difference of f with Sn, the inner product of that with Fn. So I use Cauchy-Schwarz inequality here to say that this inner product is bounded by the L2 norm of the difference of f with its nth partial sum times the L2 norm of Fn. Now this Fn is assumed to have L2 norm 1 because it comes from an orthonormal set. This norm here is exactly the norm that we assumed was going to 0. So that means that this quantity is going to 0. So the thing we started with is going to 0. But look at what we started with. We started with this integral of f against Fn, subtract the sum k equals 1 to n of ck times this integral, fk against Fn. So if you look at what that means to say that this is going to 0, that means that the limit of this partial sum is going to this integral. So that means that integral is equal to the limit as n goes to infinity of the sum k equals 1 to n of ck times the integral from a to b of fk times fn dx. So this is a partial sum. It's not the same partial sum as this s sub n here, but it's a partial sum, and it's going to this integral. Okay, well, that tells us that we're allowed to integrate term by term. And what does that give us? That gives us the reason we wanted to integrate term by term is we wanted to show that the inner product of f with fn gave us our coefficient Cn, and that gave us uniqueness. So we know that if f can be represented as a series in this way, it can be represented in only one way. But it remains to show that any f can be written as a series this way. If f has such an expansion, then it's equal to ck. Or rather, if f has an expansion, the sum k equals 1 to infinity of ck fk, then we know what the coefficients are. Ck is equal to f inner product with fk. So we know that. We also know that if it converges, if this series converges, it must converge to f. That is to say, if the series where the coefficients are made in this way. So ck is equal to the inner product of f with fk. If you construct a series this way, so we're constructing this series using f to make the coefficients. So if you do this, if you construct a series in this way, if it converges, it has to converge to f. And this follows from the fact that our orthonormal system is complete. Because to see this, suppose that g is actually equal to this sum in the L2 sense. So we're just defining this g to be equal to this sum. So at this point, we don't know that this is equal to f. We want to show that it's equal to f. We constructed this series using f. This is going to be called the generalized Fourier series of f. So we constructed this series using f to make the coefficients. Now what we would hope is that if this series converges, we would hope that that means that it actually converges to f, but we don't know that in advance. So we have a series, and we're going to assume that it does converge to something. And we want to say that that something has to be equal to f. So call it g. G is just the name that we're giving to this series, which we know converges. We're assuming converges. Okay, so g minus f, if we look at the inner product of that with fn, we can use the linearity in the first argument to say that that's equal to g at fn minus, or rather, that's equal to the inner product of g with fn minus the inner product of f with fn. But we know that the inner product of g with fn, because g is equal to a series, we know that if you have a series like this, if you look at the inner product of that series with fn, you strip off the nth coefficient, so that's equal to cn. So this g inner product with fn is equal to cn. On the other hand, we defined cn to be equal to the inner product of f with fn. That was the definition. That's how we defined ck, or cn in this case. So cn is defined to be f comma fn, or the inner product of f with fn. So what does that tell us? That tells us that the inner product of g minus f with fn is going to be equal to 0. But this is true for every fn. So g minus f must be equal to 0. Because we were assuming that this was a complete orthonormal system. So if g minus f is equal to 0, that means that g is equal to f. So f must be equal to this series in the L2 sense. When we say in the L2 sense, we just mean that this series converges to f in the L2 norm. Remember that when you're talking about an infinite sum, using the word equals is a little bit ambiguous. So when we say that f is equal to this series in the L2 sense, we just mean that this series converges to f in the L2 norm. This thing right here, we just mean that that goes to 0. So what we've done here is we've said that if this series, okay, so this series is constructed, okay, so we're writing down a series and we're constructing the coefficients using f. So the kth coefficient ck is the inner product of f with fk. So we're constructing a series that way. And we've just shown that if that series converges, it must converge to f. But there is a question here. Do we know that it converges? Do we know that the series converges? If it converges to f, but do we know that it converges? So can we show that it converges to f directly? Well, we want to show that this norm, the difference between f and its partial sum, Sn, we want to show that that goes to 0. So can we just do it directly? Can we do it by direct computation? So let's just compute it directly. So f minus its partial sum is equal to, well, so this is the norm quantity squared. So that means it's equal to the inner product with itself. Remember that the inner product of a function with itself is its norm squared. So we want to show that this norm, this L2 norm, goes to 0. So let's look at its norm squared, because if its norm squared goes to 0, then it has to go to 0 too. Okay, then the norm has to go to 0 as well. So we're looking at the norm squared. So the norm squared is equal to the inner product of the function with itself. Okay, so this is the same using the bilinearity properties and the symmetry properties. This is equal to the inner product of f with f, which is right there. And then we have the inner product of f with negative Sn, and the inner product of negative Sn with f. So we use symmetry and linearity to write that as minus 2 times the inner product of f with Sn. This is going to be the most difficult one to compute. Or no, actually, this one's the most difficult one to compute. So we have minus Sn inner product with minus Sn, which is Sn inner product with Sn. So we want to compute all of them directly, so we'll call this one A. Now that one's easy. A is just the norm of f quantity squared. Now what about B? That's the inner product of f with it. Don't forget that there's a minus 2 here, but I'm just calling B this thing. So B is just this inner product here. So that's B. So what is Sn? Sn is the partial sum. Now this is a finite partial sum, so we can just use linearity in the second argument to pull out the sum, pull out the constant coefficients here. That just leaves us with f comma fk. But we know by definition that's ck. That's the definition of ck. So we have the sum, k equals 1 to n, of ck times ck, or ck squared. Okay, so that's B. Now next we want to do C. C is the inner product of Sn with itself, right here. So let's compute that. So that's the partial sum. That's the partial sum inner product with itself. So again, we use bilinearity. Notice I'm using an index j here because I have two different sums and I don't want to get confused about which one is which. So I'm summing this one over k and summing this one over j, but it's the same thing. This is C1 F1 plus C2 F2 plus C3 F3. They're both the same thing. And the last term is Cn Fn. Okay. So again, I'm going to use bilinearity to pull out the sums and the constants. So that just leaves us with the sum k equals 1 to n, sum j equals 1 to n, ckcj times the inner product of fk with fj. But this quantity is equal to 0 unless k is equal to j. So that means it might look like there's a double sum here, but there's really only one sum, because if you look at this inner sum is always, every term is 0 except for one, the one where c is equal, where j is equal to k. So that means all of this outer sum here, or the inner sum rather. So this inner sum, there's only one non-zero term there. That's where j is equal to k. So you end up with ck times ck, which is ck squared, and then you have the inner product of fk with itself. So that's just going to be 1 because this is an orthonormal set, orthonormal system. So that's just equal to 1. So you just end up with this sum, k equals 1 to n, of ck squared. Okay, so let's put all of this back together. So we have, we're computing, oops, wrong thing. We're computing the L2 norm squared of f minus its partial sum. So f minus its partial sum, L2 norm squared. So it's equal to a, which is the inner product of f with itself. So that's this one right here. Minus 2 times b, which we just showed. This one is b, so that's right there. Don't forget the minus 2 term, which is right there. And then finally, we have c, which is right here. Okay. So we have the norm of f squared minus 2 times the sum of ck squareds plus 1 sum of ck squareds. So minus 2 plus 1 just gives you a minus 1. So what that tells us, what does that tell us? If you compute the norm squared of f minus Sn, that's equal to the norm of f squared minus the sum k equals 1 to n of ck squared. Now what we know is we know that the norm squared is positive. So that means it follows that this difference is positive. So the norm of f squared minus the sum k equals 1 to n of ck squared, this object, which is equal to the norm squared, we know that that's positive, or at least non-zero. It's a non-negative. So that tells us that this difference, the norm of f quantity squared minus the sum of these ck squareds, we know that that's greater than or equal to 0. Or the norm of f quantity squared is greater than the sum k equals 1 to n of ck squared for all n. So this gives us an important result known as Bessel's inequality. And I've just summarized it here, but it's just the same thing. Since this is true for every n, in particular, and this is an increasing sequence, if you look, as n increases, the ck squareds, these are always positive. So as you start adding in more terms, you just get an increasing sequence. So the terms are increasing, the sum is increasing, but it's bounded above. So in particular, what that tells us is that this series does converge, and it's bounded by the L2 norm of f quantity squared. So we can use this to prove that Sn converges to f. We can use this fact. But we have to use a significant fact that what we call a Cauchy sequence in L2 converges to a function in L2. Now, a sequence is called Cauchy, or it's called a Cauchy sequence, provided that the terms are eventually arbitrarily close to each other. So to be precise, we say that a sequence Sn is a Cauchy sequence if for any epsilon greater than 0, there exists some k, some capital K, such that the difference between Sn and Sm is less than epsilon whenever n is bigger than k and m is bigger than k. So basically the idea here is epsilon is measuring a distance. So I want to say that these terms are getting arbitrarily close together, so I have to measure that with something. So give me any distance at all. So you give me some distance, just any distance at all, and my claim is that the terms are eventually smaller than that given distance, that prescribed distance. And when I say eventually, that means I can find some point. When I say point, I mean I can find some index. I can find some index so that all of the terms that occur later are so close together that they're less than that arbitrary prescribed distance that you gave me. Okay, so in L2, any Cauchy sequence converges to a limit in L2. This property is called completeness. Now, not every space is complete. The real numbers are complete. So if you find any sequence of real numbers which are a Cauchy sequence, so that means all of the terms are getting close to one another, that means they converge to a limit. But it's not necessarily true, for example, if you restrict your attention to rational numbers. If you look at a sequence of rational numbers, they might converge to an irrational number. So the set of rational numbers is not a complete set, but the set of real numbers is a complete set. Now, L2 is a complete set. Now, this is something that we're not going to be able to show, but it is a complete set. And so what that means is that if you find a sequence in L2 so that all of the terms are getting arbitrarily close to each other, then that sequence must converge to some function in L2. So we'll just take that for granted. Now, since we know that this infinite series converges to some number b, that means the distance between this partial sum, the sum k equals 1 to k, capital K, of ck squared, and b can be made arbitrarily small. So that is, for any epsilon, we can find some number capital K such that this difference is less than epsilon. Now notice what this is. This is just the sum of the tail. This is the tail of the series. The sum lowercase k equals capital K plus 1 to infinity of ck squared. So this is the tail. This is the tail. So the idea is that since the series converges, this tail must get arbitrarily small. Okay, so observe that for any n and m bigger than k, say n bigger than m bigger than k, we can actually compute this difference of these partial sums. So that's the sum, the partial sum to n minus the partial sum to m, and we're looking at the L2 norm squared. So that's equal to the sum lowercase k equals capital M plus 1 to n of ck fk. But again, this is the norm squared, so you can write that as the inner product of the function with itself. And once again, you use bilinearity. And once again, we have ckcj times the inner product of fk with fj. But just like before, this quantity is equal to 0 if k is not equal to j, and it's equal to 1 if k is equal to j. So this doubly infinite sum is really just one sum, and it's the sum of ck times ck, or ck squared. Now here we're adding together ck squared for k equals m plus 1 to n. Now that's certainly a subset of the indices in the tail. So this is less than the sum of the ck squareds going from k plus 1 to infinity. And we assumed that, or we didn't assume, but we assumed that there was some k, or rather, we assumed that k was the number, capital K was the number, so that this tail was less than epsilon. Now all of this is relying on the fact that these ck squareds are positive. So here I'm adding together a bunch of terms, but I'm adding together fewer terms than I do here. And since all of those terms are positive, if I add together these terms, that's going to be less than adding together even more terms. But this is the tail, which is less than epsilon. It's arbitrarily small. So what does that mean? That means that the terms in this sequence are getting arbitrarily close to one another. So eventually, all of these terms are as close together as you want them to be. And since this L2 space is complete, it implies that Sn converges to some function in L2. So that limit must be f, as we showed above. So what that means is that this series does converge in L2, and it must converge to f. This is really what we wanted to prove. We showed that if we started with a function in L2, and we constructed this infinite series where ck was equal to the inner product of f with fk, then we get an infinite series which converges to f in L2. And that's what we wanted. We showed that the series converges, and it converges to F. Converges in the L2 sense. Okay, so what else did we show? We also showed a very interesting equality. Earlier, we saw that if you looked at the difference of F with its partial sum, as you see here, if you looked at that difference in norm squared, that was equal to the norm of F squared minus the sum k equals 1 to n of ck squared. Since we now know that Sn goes to F in L2, that means that this norm goes to 0 as n goes to infinity. As n goes to infinity, capital N. So that means that this difference goes to 0. But we know that this series converges. That series converges to the sum of k equals 1 to infinity of ck squared. So if we know that this difference goes to 0, and we know that this sum converges, we know that that sum converges to the norm of f, quantity squared. So this is a result which is known as Parsifal's equality, or Parsifal's identity. And the statement is simply that the square norm, or the L2 norm quantity squared of f, is equal to the sum, k equals 1 to infinity of ck squared, where the ck's are given in this way. So it's the inner product of f with fk, and fk is a complete orthonormal system. This result is true only when fk is complete. Otherwise, the best you can say is that the infinite sum is less than or equal to the L2 norm squared, which is what we called Bessel's inequality above. Okay, let's give some names to these things. So suppose that fk is an orthogonal, well, I guess we should make it an orthonormal system. So suppose that fk is an orthonormal system in L2. If f is a function in L2, and ck is equal to the inner product of f with fk for each k and n, then the series that we create, the sum k equals 1 to infinity of ck fk, is called the generalized Fourier series for f, or just the Fourier series for f. And ck are called the Fourier coefficients. When ab is equal to minus l to l, so when the interval from a to b is a symmetric interval about the origin from minus l to l, where l is some positive number, and the orthogonal system consists of these trigonometric functions, then we call the series that you construct in this way the classical Fourier series, or trigonometric series. Now, actually, the way that I've done it, this is an orthogonal system, so we actually need to divide by the length of these things. So we should normalize. We should normalize those. And then we'll get the classical Fourier series, or what's called trigonometric series. We'll just call it the Fourier series. We won't worry too much about calling it the classical Fourier series. We'll just call it Fourier series. But it's very common to call it trigonometric series because of the presence of these trigonometric functions. Let's make some remarks here. The Fourier series for f converges to f in L2, but may not converge to f pointwise. Under certain conditions, we'll see that the Fourier series does converge pointwise, and those conditions we'll encounter usually, most of the time, just not always. The second remark is that the Fourier series for f gives what we call the best approximation to f in L2, in the sense that any other approximation in L2 will have a larger mean square error. To be precise, if you let f1 to fn be a finite orthonormal system in L2, and let ck be the Fourier coefficients for each k in the set from 1 to n, and if a1 to an is any other set of n coefficients, then the mean square error between f and the partial sum using the Fourier coefficients is going to be smaller than the mean square error using these other coefficients. This is not hard to prove. If you go back through the computations that we've done already, you can see that this will come out pretty easily. You can also find it in the book if you want to look through it. So our last comment here is about a third type of convergence, which is called uniform convergence. We say that Sn converges to F uniformly if the pointwise error goes to 0, but not pointwise. If you look at the maximum of the pointwise errors, then that goes to 0. So this is actually a very strong form of convergence because it requires the maximum error, which we call epsilon sub n, over AB to go to 0. Notice that this term right here, that's the pointwise error. But it's not just the pointwise error we're looking at the maximum. So for a given n, you look at the pointwise error at each x, and then you pick the maximum of all of those. Now you might need to replace maximum with supremum in case that the maximum is not actually attained. If these functions are continuous, and this is a closed interval, then it will attain its maximum. But you can relax the restrictions. Your functions need not be continuous, and you might actually look at a non-closed interval. So what you do is you look at each x, and so you fixed an n, and then you look at the error, the pointwise error for each x, and then you collect all of those together and you look at the maximum. Now that's what we call epsilon n, so that's the maximum error over AB. And in order for convergence to be uniform, this maximum error has to go to 0 as capital N goes to infinity. This is a very strong form of convergence. So for example, suppose that you computed the pointwise errors and you found that the pointwise error at x for a given n was 1 over xn. Then for each x, epsilon x, not epsilon, let me say that again. So let's suppose that we've shown that the pointwise error for n is 1 over xn. Then if you fix an x, then the limit of the pointwise error at that x goes to 0. Because this quantity, if you fix an x, this quantity is going to 0 as n goes to infinity. But in order for the pointwise error to be less than some arbitrary number epsilon, some arbitrary error, some specified amount epsilon, you need 1 over xn to be less than epsilon. Or in other words, you need n to be bigger than 1 over x epsilon. So in particular, what that means is it depends on your x value. In order for something to converge to 0 uniformly, then it needs to, the n value can't depend on x. It has to, you need to be able to use the same n value for every x. But if you suppose that you're looking at x in an interval from 0 to 1, where of course you don't include 0, so this isn't a closed interval. So if you're looking at the open interval from 0 to 1, then this n must be larger for x closer to 0. So what that means is that this value is infinite. So again, this really shouldn't be maximum, this should be supremum here. You only call it maximum if it actually attains the maximum. So uniform convergence is a very strong form of convergence, which we cannot ensure, not always. It's hard enough to ensure pointwise convergence. But we'll see, or at least we'll mention conditions that will ensure pointwise convergence and uniform convergence. But what we do definitely have is we have that the Fourier series converges to f. I should say the Fourier series of a function f converges to f in L2. In terms of the mean square error, we do have convergence. So sometimes that will be good enough for our purposes.